if you define God as the creator,
Yes.
then you're right. From some point that we don't understand, by the way, the Big Bang, we don't even understand whether that was the origin of the universe, by the way. We understand that something interesting happened, infinite cyclical universe.
Yes.
And he's trying to answer questions about the very special state of the early universe and why it was the way that it was. It doesn't really contract. It's called, what's it called? Conformal cosmology, or cyclical conformal cosmology or something. So it's essentially that, and I don't fully understand it, and I have asked him about it with some colleagues. No, I don't think many of us understand what Roger Penrose is one of the greats, right? So you listen to him and take him very seriously. But I haven't met anyone who quite understands what he's talking about in that. But it doesn't recontract. It's not one of those models where the universe expands and then recontracts and bounces like that. It's not one of those. It's somehow, he argues, that when you get to what we usually call the heat death of the universe, where even the black holes have evaporated away, you have conditions that begin to look perhaps like an origin of the universe again. And I can't really fully explain it because I don't really understand what he's kind of looks like. Conformal means there are no sort of distances or time measurements or anything in the universe. It kind of loses all sense of scale, and then you could reimagine that as looking somewhat like the beginning. It's something like that he has in mind, but I really couldn't explain to you. I don't understand what he's proposing.
Wow.
There. So what it does tell you is that we don't know why or how the universe got into the state that we call the Big Bang. So we don't know whether the universe existed before that. We have theories that it did, theories called inflation, which are very popular theories. You'll find them in all the textbooks, which say that before the universe was hot and dense, which we used to call the Big Bang, space and time is still there, and the universe is expanding extremely fast. It's called inflation. And then that period draws to a close, and that expansion sort of slows down and almost collapses and changes, and the energy that was driving the expansion gets sort of dumped into space and changes and ultimately makes the particles out of which we are made. So that's actually the standard model of cosmology now. So we do have an idea that we redefine the Big Bang as the hot Big Bang, and it's not the origin of the universe in time. It's the end of inflation. And then you get the question, what is inflation? Did that have a beginning? And the answer is that in Einstein's theory alone, then yes. And Roger Penrose actually and Stephen Hawking proved this a long time ago, that just given Einstein's theory, you have this singularity, just kind of like the black hole singularity, but at the beginning of time. But we do know that when you put quantum mechanics in and add that in, then it gets messy and we don't really know what that means. And so Stephen Hawking had a thing called the no boundary proposal. There's all sorts. Basically, the point is we don't know. So we don't know whether the universe had a beginning in time, I would say is the correct statement as we are at the moment. It's part of the reason why, by the way, getting back to the black holes, they're important and interesting. Because the study of black holes and this idea of information and how does it get out, that's leading us to suspect that space and time themselves are not fundamental, but they emerge from something else. So just in the way that we've been talking about consciousness emerging from this physical structure in our heads. So we don't know how it emerges, it's a very strange thing, but it emerges from this collection of atoms, right, in a particular pattern. Well, we think now, from the study of black holes, that space and time emerge from something else, which is kind of, one way to describe it is just a quantum theory. So it's in quantum computing terms, it would be just qubits. So a network of qubits entangled together, just like a quantum computer. Out of that, we suspect that space and time might emerge. So surely we have to understand that process, and we don't really fully understand that, but we have glimpses of it in much more detail to start talking about the origin of time. Because in order to talk about the origin of time, you have to know what it is. And we don't actually know what it is, which is, and that's kind of, when you say that, it sounds bizarre, doesn't it? Well, how can you not know what time is? I think Einstein once said that it is the thing that you measure on a watch. But he said that as kind of almost a joke, because you assume in Einstein's theory there's a thing that the watch measures. But what actually it is, at the deepest level, is a good question. So, but it's funny, it's interesting that study of black holes is forcing us towards these theories. It's not that we had the theory, space and time emerging from something, and decided we could check it by thinking about black holes. It's come the other way round, really. So it's interesting. But that almost makes the universe look, in some ways, like a giant quantum computer, which is not to say that we live in a simulation, before you ask. But it just looks like there's a description of the universe that looks like a quantum computer type description. Now, that doesn't have the concept of space or time in it. It's interesting that you're right, and that's a good way of phrasing it. Mimics or looks like a network of qubits. So it looks like some kind of quantum computing description is available to us for the universe. It's right to say that Einstein really felt, I think, that initially that an eternal universe was more natural. But it is also true to say that his theory, general relativity, really doesn't quite rule that out, but it's strongly suggestive of there being a beginning and or an end. So the theory itself, historically speaking, strongly suggests that. And so he changed his mind. And then we saw the universe was expanding, we observed that. And then we've now seen the oldest light in the universe, the cosmic microwave background radiation, which is the afterglow of the Big Bang. So we know that the universe was hot and dense 13.8 billion years ago. We have so much evidence for that, not least that we have a photograph of it 380,000 years after the Big Bang. It's called the cosmic microwave background.
Let's see that. Let me see that
we have
photo.
Images of that. That's from the satellite called Planck, a European satellite, and also a satellite called COBE. So we have these images of the afterglow of the Big Bang. We also have theories that tell us about the abundance of chemical elements in the universe, which match this perfectly. So there's multiple lines of evidence that tell us the universe was hot and dense. But none of that tells us that was the beginning. That I think that would be widely accepted. That it's a beginning in Einstein's theory. If you just take general relativity, there's a singularity there at the beginning of time. We don't know what it is, but it's there. But it absolutely is true to say that we think that's not complete as a picture. So there it is. So that is light that was emitted about 380,000 years after the Big Bang. So and the key thing, there's so many things to say about these images, but one thing is that those colours correspond to regions of very slightly different density that we've detected now in the gases of the young universe.
Are you talking about the red, blue?
Yeah, the reds and blues, those or those as well. They're both the same. So that greeny one, well, either that one or the one with the greeny blue, that one, that's from the Planck satellite. So those colours correspond to regions of different density. So in this young universe, 380,000 years after the Big Bang, that's only hydrogen and helium gas, basically, and a bit of lithium, some of the lighter elements, but basically hydrogen and helium. So you've got an almost smooth, almost featureless universe then. But these little density fluctuations are very important, because as the universe expanded and cooled, they collapsed to form the galaxies. So without those ripples, without that pattern, we would not exist. Nothing of interest would exist. And so the question is, where did that come from, that pattern? It's fundamentally important. And the theory of inflation that I mentioned earlier, that there's this time before the universe got hot and dense, that theory predicted that pattern before it was observed. So this idea that you've got this very quickly stretching space. And by the way, the stretch, if I can remember the number, is if you consider 2 points in space during inflation, the distance between them was doubling every 10 to the minus 37 seconds, which is 0.00000, which is 37 noughts, one of a second. So it's incredible rate of expansion that draws to a close. And those theories, so there's inflation there. So those theories predicted slight variations in the rate at which inflation stops. There are a lot of things about the universe that I find it almost impossible to imagine. Well, actually impossible to imagine. One's just the size and scale of it. I mean, in the piece of the universe we can see, there are something like, roughly, 2 trillion galaxies. We haven't counted them all, but that's an estimate based on surveys of the local universe. 2 trillion, 2,000 billion galaxies. And each galaxy is, let's say, around the size of the Milky Way. Some are bigger, some are smaller, but the Milky Way has 400 billion stars in it. It takes light over 100,000 years to cross a galaxy. And there are 2 trillion of them in the piece of the universe we can see. And we're very sure that that piece that we can see is a small bit of what may be an infinite universe beyond. We don't know, actually. And I always say, don't get worried about that, because nobody can picture it. It is impossible to visualize the scale of the universe. So that's the first thing. I could then list a lot of more things, but we'll stop there for now. But just the size and scale of it, I think, is beyond imagination. And that is a very good question. The 1 minute answer is we don't know. So one of our theories is that space and time, for that matter. So I should say, back in 1905, Einstein realised that space and time are not separate, but they're woven together into something that's often called the fabric of the universe, or more technically, space-time. But we now suspect, or at least we have a theory, that space-time emerges from something deeper, which is just basically quantum entanglement. So we think that there is a description of our universe which is just bits of information, basically, or qubits to be more technical, quantum bits of information that are entangled together into some sort of network, so space and time don't exist in that network, and then space and time emerge from that deeper theory. This is cutting-edge physics, but it's one of the pictures that we have for what space and time might be. Often is the case with science questions. There's not complete agreement, but there is a theory with which most people agree, which is that it was made in an impact. So very early on in the life of the solar system, so let's say 4.5 billion years ago or so, we think that a planet about the size of Mars collided with the young Earth. And it's a glancing blow, actually, which caused a lot of rubble to go out into space, formed momentarily a ring around the Earth, somewhat like the rings around Saturn, but then that ring very quickly coalesced into the Moon. So we think that the Moon is made of mainly bits of the Earth and also bits of this other planet that glanced off it about, I'm not sure of the exact date, I think it's something like 4.5 billion years ago. It's very, very early, very soon after the Earth formed. So I say sometimes in my live shows, it's kind of a joke, right? So I'm not insulting philosophers here, but I say there's only one interesting question in philosophy, right? And I don't really mean it, but I think it sounds funny. So the interesting question is, what does it mean to live a finite, fragile life in an infinite, eternal universe? So that's not that funny, right? It's a good question. What does it mean to live a finite, fragile life in an infinite, eternal universe? And I think the answer is that, sort of paradoxically, whilst we are definitely physically insignificant, I've just said, that the Earth is one star around the Earth is one planet around one star amongst 400 billion stars in one galaxy amongst 2 trillion galaxies in a small patch of the universe, right? So we're definitely small, and you can't argue with that. We're just specks of dust. But if you think about what we are, so everybody, me and you, everybody, we're just collections of atoms, right? Some of them are as old as time, pretty much, and some of them were the other ones. Everything else, other than the hydrogen in our bodies, was made in stars, right? So we're all cooked over billions of years. And we're in this pattern that can think. So suddenly, as the great Carl Sagan said, you have a means by which the universe understands and explores itself, which is us. And that sounds unlikely when you put it like that, that you can have a few things that were cooked in the hearts of stars, you stick them together in a pattern, and suddenly it has some ideas and starts writing music and art and things. That's quite difficult to comprehend, right? But that happened here, We know that because we're sat here having a conversation. And so the question then becomes, well, on how many other worlds did that happen? And that's where I think the value can come in, because it's a reasonable guess, and it's just a guess, right? But it's reasonable. You can make the argument that there aren't any other worlds where this happened, certainly in our galaxy. So it could be that this planet, notwithstanding its physical insignificance, is the only place where anything thinks, right? For millions of light years in every direction. And suddenly, therefore, you end up considering this planet as being the most valuable place in the local universe, notwithstanding the fact that it's small. And that idea, it's not just a complete random guess, by the way. We've had a bit of a look. Astronomers have pointed radio telescopes up at the stars for a while, 50 years or more now, and heard nothing. We've seen no evidence of any civilizations out there beyond Earth, and that's a surprise. There's a reasonably plausible explanation for that, which is biology, which is that if you look at the history of life on Earth, then you see that life began pretty much as soon as it could here on Earth. We have evidence there was life 3.8 billion years ago, something like that, and the Earth's 4.5 billion years old, so pretty quick in geological time you get life. But then if you talk about advanced life, complex life, multicellular life, then there's no evidence at all back beyond a billion years. Actually, really, in the fossil record, 650 million years ago or something, you start seeing the first evidence of complex creatures. So that means that on this planet, it took over 3 billion years to go from a single cell life to anything more complex than a single cell. And then another 500 million years or so to go from the multicellular things to a civilization. So it's 3.5 to 4 billion years. It's a third of the age of the universe. That is a really long time. If you say that's an unbroken chain of life on a little piece of rock in a violent universe, and that chain was not cut for 4 billion years in order to get us. And that might be a big ask, right? We live in a really violent universe. You look at the Milky Way and you look at that arc of stars across the sky, 400 billion suns. All there will be up there at best is slime. It's just slime. Nothing, right? And I think that's a reasonable guess. That's where I start from. I mean, I wouldn't be surprised if that's wrong. Then you go, okay, good, well, fine. But at the moment, it looks like there isn't anything else other than slime. We haven't even discovered slime, by the way, yet. We're still in the position where we've not seen anything, not even a single cell on Mars or the moons of Jupiter or somewhere like that. So at the moment, we are alone, as far as we can tell.
Oh, that's a good question. I don't know the figure for the biggest star, but one of the biggest you can see with the naked eye actually is Betelgeuse or Betelgeuse in Orion. And that's the red star in the constellation of Orion. I sort of want to say, but I can't because the orientation's different here, but it's a top left, but it's not. It's going to rotate it over.
Just tilt your head. Yeah.
Go and find Betelgeuse. It's a red star in Orion, the shoulder of Orion. And what's interesting about that is if you put it where the Earth is, then it would extend out pretty much to the orbit of Jupiter, I think even beyond the orbit of Jupiter. So if you imagine how far it is to Jupiter, that would be orbiting inside the star. And it's so big that we can see sunspots on the surface with telescopes here on Earth. So it's a vast star. But that's a star at the end of its life that's swollen up. That isn't, however, the biggest. So what we should probably do is that I should go onto the internet and look up. I don't have in my head the number for the most massive star or the biggest star. But there are stars that are really, literally the size of solar systems. Yeah, well, they have very short lifetimes. That's the thing. So the more massive the star is, so you're talking about, as you said, a star, let's say 10,000 times the mass of the sun, then it has to burn its fuel extremely quickly to stay up against the force of gravity. And so they live for millions of years, actually, the lifetimes, not billions of years. So they're very, very, very short-lived, the really massive stars in the universe. So the number of stars you can see, first of all, is actually only a few thousand, I think. It obviously depends on how big the telescope is that you have. All of the stars we can see are in our galaxy. The only thing you can see beyond our galaxy, well, there are three things in the southern hemisphere. You can see the Magellanic Clouds, which are satellite galaxies of the Milky Way, and you can also see Andromeda with the naked eye. And that's pretty much all you can see beyond our galaxy without binoculars or a telescope. You get some good binoculars and you start to see tens of galaxies, or even a small telescope, you can start to see tens or even hundreds of galaxies out there. The number of stars in the universe, so there are something like between 200 and 400 billion stars in our galaxy. And you might think that's why, it's not because I don't know, it's because nobody knows. It's quite hard to count, actually. So it changes all the time, the estimate. But let's say, conservatively, 200 billion, that's 200,000 million stars in our galaxy. And the current estimate for the number of galaxies in the observable universe, which is the bit we can see, is around 2 trillion. So that's 2 million. Yeah, that's right, 2 million. So we have something like, let's say, 2 million galaxies that we can see in principle. And each one of those has 200,000 million stars, let's say, on average. So you have to multiply 2 million by 2,000 million. So that's a 6 and a 6 and a 6, that's 18, 19, 20, 21. So it's something like, let's say, 4 with 21 noughts after it. So that's a 2 with 12 noughts after it. Mm-hmm. And then we have let's say a 2 with 9 noughts after it. So it's a 12 and a 9, so that's 21 noughts and probably 4 or 5. So let's say 22. So let's say 1 with 22 noughts after it, something like that. However, that's the bit of the universe we can see in principle. It's called the observable universe. We very strongly suspect that the universe extends way beyond the bit we can see. It does, for all intents and purposes. And we don't know how big it is. So it could go on forever. We just don't know. These are big numbers.
These questions we have about our place. And as you said, it can be easy to be myopic, can't it? Yes. You said if you look at our screens, it's Earth that we think about at most. And most of us don't really think about Earth. You think about your country or your city or your town.
Or your neighborhood.
Even think about the Earth. But you're right. If you know, when you look at that arc of stars, and as you said, when you see it in a truly dark sky, it's powerful.
It's incredible. 400
billion suns, give or take. 400,000 million suns. It's impossible to picture. And most of them, I think the best guess would be all of them have planets. So pretty much. So you're talking about trillions of planets.
Now we're getting into my subjects.
No, I mean, the thing is, there's a thing called the Fermi paradox.
Yes.
Which I think we talked about before on the show.
Yes.
And the paradox is that if we haven't seen it, let's assume we haven't seen any evidence of anything. That's a paradox. Because as I said, we now know, we didn't when Fermi first posed it, by the way, we now know there are so many planets out there. So let's say trillions of planets in the Milky Way. The Milky Way's been there for over 13 billion years, pretty much the age of the universe. So if there's no one else out there, then the question is why? Because there's been so much time and so many places for civilizations to become spacefaring civilizations.
Right.
As Elon talks about, multiplanetary civilization, we're very close to becoming a multiplanetary civilization. And once you have become a multiplanetary and multistellar civilization, if you become that, you're immortal, basically, essentially.
Right.
So the question is, the paradox is, why does it appear nobody has done that? So the first thing to say is, I would not be surprised, right? If a UFO landed here now in the parking lot, I'd actually, not only would I not be surprised, I'd be relieved, actually. Because I'd be like, this is good, because it'd be a weight off my shoulders, because I'm worried
that we're the only ones.
That's
a terrifying scenario.
And we're going to make a mess of it.
Yeah.
And so I'm worried that we could talk about that.
But isn't it bizarre? Like,
that we're the only ones in our galaxy, let's say.
Okay.
Then I would argue that, so there's a question I ask in these live shows that I do. I start with a question which is kind of a joke in a way, which is what does it mean to live a finite, fragile life in an infinite, eternal universe? Which is a good question, right? That's what you're asking.
Yeah,
right?
that's
What does it
the real
mean
question.
to live this finite?
Right.
The first thing to say is meaning, right? What does it mean? That doesn't sound like a scientific concept in a way. Meaning,
Right.
I would argue that whatever it is, it self-evidently exists because the universe means something to us. I would argue that it's a property of complex biological systems. So whatever it is, it's something that emerges, in this case, from human brains. It self-evidently exists. Everyone who's listening to this knows that the world means something to them. So I would argue that if this planet is the only planet in our galaxy where complex biological systems exist, right, at our level, then it follows it's the only place where meaning currently exists in a galaxy of 400 billion suns. And therefore, I would argue, just for that very basic point, that we have a tremendous responsibility in some sense. Because by the way, I gave a talk, a little video thing at one of the climate summit, the COP climate summit in Glasgow in the UK a few years ago. And they asked me to do a little video to the world leaders. And I think they thought I'd say, welcome to Glasgow, have a nice meeting. But I made this little argument as fast as I could. I said it's possible, at least, that this is the only place where complex biology has emerged in our galaxy. If that's true, this is the only island of meaning in a galaxy of 400 billion suns, and you are responsible for it because you are the world leaders. Therefore, if you destroy it through deliberate action or inaction, then each of you would be personally responsible for destroying meaning in a galaxy of 400 billion suns, potentially forever. Now go and discuss that. Was my intro to Glasgow. Now, and we can all argue, because people will be listening to this going, this nonsense, how can it be? We can all argue about whether that's true. What I would say is, given that, as far as I'm aware, we don't have any good evidence to the contrary, which goes back to your previous question, it's a reasonable working assumption. So why don't we just operate on that basis? And then, if someone lands tomorrow, as I said, I'd be very delighted, because then what I just said would be false. And we could relax a bit and go, it doesn't really matter if we destroy ourselves to some extent. But so I think it's worth taking seriously the idea that civilizations are very rare. Now, and by the way, I used to say, so I probably last time I was on actually, complex life will cease to exist. So it probably doesn't matter on a global scale, but it matters locally because of this idea that meaning emerges from complex biological systems. So if you don't care about that, what do you care about? That it's not necessarily true that life is temporary, because you could imagine a situation as you go into the far future. Let's imagine that we continue for 1 million years or 1 billion years as a civilization. Imagine what we could do. It is possible that life can get so advanced in the universe that it can start to manipulate the universe itself. So, or at least stars. You could he said you could imagine, for example, just imagine, really wild speculation, but imagine life gets so advanced that it can start to change the destiny of a star. Maybe it could start to add material into the star or something, whatever. So we don't know how to do that or if it's possible, but imagine it could. Then the evolution of stars life would matter in the sense that it could start to change the way that the universe behaves on a large scale in the future. And so it reminded me, actually, there's another great book by John Barrow and Frank Tipler called The Anthropic Cosmological Principle from the 1980s. It's one of my favourite books, actually. And I remembered it. And in there, they speculate about this life in the far, far future. And if it became powerful enough to manipulate the whole universe, or the observable universe, then suddenly you can't make predictions about the far future unless you consider the possible impact of life on the universe. And whilst this is, I should say, it's wildly speculative, but it's actually logically, it's quite an interesting point. So I kind of disagree with myself a few years ago, where I would have said that life is extremely valuable because it brings meaning to the universe, but temporarily. And so it brings these brief, like flickering candles of meaning, and then they go out again. But it's worth considering. It might not necessarily be true that if you really think. I mean, just to say, I mean, it must sound to many people listening just nonsense, right? Science fiction. But if you think our civilization has been around for, 10,000 years at best, really, give or take. And in that time, we've sent stuff out of the solar system. Although we don't yet, we're way away from being able to manipulate stars, we can manipulate planets. So we are changing the way this planet operates. Life has changed it. The oxygen in the atmosphere, before we appeared, the oxygen in the atmosphere is a product of life. So life already, we know, changes planets. And so I like that speculation that possibly, it's not just a temporary little phenomena that flickers in and out and then disappears again. It could have a real bearing on the future of the universe. Well, exactly. And this is the point that David Deutsch made in the book I've just been reading, and John Barrow and Frank Tipler made before that although it sounds insane, as you said, and that 4 billion years, there's a lot to say about that, by the way, because for 3 billion plus years of that on this planet, it was just single cells. And so it's only in the last, let's say, 1 billion years, but actually a bit less, that we've had multicellular organisms. So 3/4 of it of the time were just single-celled things.
That's even crazier.
So, which is one of the reasons that many people think civilizations might be rare. Because if you the only evidence we have is this planet.
Right.
And the evidence on this planet is that single-celled life is sort of the way that things are for most of the history. And then, so it seems like an accident, in a way, that happened late on in the history of life on Earth that produced multicellular life. Now, whether is that typical? We don't know. Maybe it took a longer time here than it might do somewhere else. But if it's typical, 4 billion years, you said it's not a long time. It is a third of the age of the universe. So here,
when you put it that way, it's a long time.
1/3 of the age of the universe to go from the origin of life to a civilization. And so what was required here on Earth was that unbroken chain of life remained unbroken for a third of the age of the universe in a violent universe. We know there are impacts from space. Many stars are significantly more active than the sun. So the sun's kind of quite a boring little star that just ticks along. It's very nice to us. We're also on the edge of the galaxy, by the way. We're not close in. If you go into this region where that black hole is, there are a lot of stars around. There are supernova explosions and all sorts of stuff going on. So it's violent in there. So maybe you can only get unbroken chains of life for billions of years on the outskirts of a galaxy. So there are fewer stars and planets out there. And maybe even then you need to be fortunate.
Well, also, aren't we very unusual in the size of our moon and the distance?
The moon, it is big, and so it stabilizes the spin. So the spin axis, Mars, I think, if I'm right, I think the spin axis has wobbled around by something like 60 degrees or something over its history.
So, what you mean by probability favours the existence of aliens, I guess you mean, and I'd agree with you, that the universe is so big. We just said that there is something like 1 with 22 noughts after its stars in the observable universe. We now know that most of those have planetary systems. Certainly, if you look in the Milky Way, which we can do in our own galaxy, basically everywhere we look, we find planets around the stars. So let's say that most of them have solar systems. So it is inconceivable that there will not be life and I think civilizations out there amongst the stars. But the question becomes, first of all, what form does that life take? So in the solar system, we know there's only one place, Earth, which has complex life and certainly a civilization like ours. It could well be that there are microbes below the surface on Mars today, or there may have been microbes on Mars in the past when Mars had rivers and lakes and quite possibly oceans for a few 100 million years. So there could have been Martians, but they would have been little microbes or bacteria-like things at best, I think. On the moons of Jupiter and Saturn, like Europa, there are oceans below the surface, and we think the conditions are right for life to have started, but we don't know because we haven't been there. So if there are aliens in our solar system, there'll be little single-celled things waiting for us to find them. Some of you might discover them actually, because we are building missions to Mars. We'll be sending humans to Mars, certainly in your lifetime. And one of the things you'll be doing is looking for microbes below the surface. So maybe we'll find Martians. But if you mean aliens in spaceships, that means civilizations. We don't know. We've looked a bit. We've listened for radio signals from other stars. We've found nothing. We have no evidence of alien civilizations at all. That might mean we haven't looked hard enough, because we haven't looked particularly hard. The galaxy is very big. But it might also mean that civilizations are rare. And the one thing I would say is that if you speak to biologists, they will be more pessimistic about discovering civilizations than astronomers, I think. Astronomers tend to say, don't they, there's loads of planets, loads of planets, there must be some. But biologists say, well, but if you look at life on Earth, it began, we have good evidence, it was on the planet, let's say 3.8 billion years ago. So let's say it may have begun even 4 billion years ago, after the planet settled down and the oceans first formed. It took 4 billion years, let's say, to go from the origin of life to a civilization, which is about a third of the age of the universe. And if you start to say, well, if that's typical and we don't know, then it may be that there are very few solar systems and planets and stars that are stable enough for that long to allow for evolution to do its work, and for the single-celled things to go to multicellular creatures and plants and make an oxygen atmosphere and then make a civilization, get some things that are clever enough. I mean, you think about it, there are clever things on Earth besides humans, dolphins, for example, but dolphins are not going to build spaceships because they can't have any electricity, because they live in the sea. And so, it could be that quite typically, if things with big brains tend to be under the water, then they're never going to build radio telescopes and spaceships. They won't be astronomers. So if civilizations exist, then yes, we could. Again, the distances are important. If you think about our galaxy, it's, let's say, 100,000 light years across or so. That means that it would take a radio signal 100,000 years to go from one end to the other. So it would be a very slow conversation. Even our nearest star, Alpha Centauri, the nearest star system, with planets around it, we think, is 4 light years away or so. So that means that a conversation would take 8 years. So if you said hello, you'd have to wait for 8 years before they said hello back. And that's our nearest star system. So the distances tend to make conversation difficult. So the first answer is, I don't think we know when the Milky Way and Andromeda collide whether the black holes will merge. I mean, we certainly know there's an interaction between the galaxies. We know the galaxies will merge. So my guess, not actually knowing the latest research, is they probably would eventually, I think. But it depends on the angle that they hit each other and so on and so on. And also the timescales. I mean, it may be that they'll inevitably merge in trillions of years, but not billions. I don't know.
Eventually they will, but it could be billions, it could be trillions. Yeah.
So, right. So maybe the consensus here is that they will do eventually, but it depends what you mean by eventually. So it might be a very, very
long you want to wait. Yeah.
But we do know what happens when black holes collide because we've observed it. So our latest detectors, which so-called gravitational wave detectors, which detect unbelievably ripples in the fabric of the universe, ripples in space and time from the collision of objects like black holes, are now working beautifully. And we've seen several occurrences in the universe where black holes have collided with each other and merged. And so what we know is that they form a black hole. They lose some energy when they collide, but they do form a black hole with an area, a surface area which is bigger than the two holes that collide. And that was a prediction from Stephen Hawking, the so-called area theorem. And that's been proved. So, and the prediction of how they collide and how they merge and what you get afterwards is in absolute accord with Einstein's theory of general relativity, which was published over 100 years ago. And Einstein didn't know that there were such things as black holes when he published the theory. He certainly didn't know that we'd ever see them collide together. He certainly didn't know that there were ripples in the fabric of the cosmos, although he predicted that slightly later, that would carry the information, just like light carries the information from distant stars, so the ripples in the universe can carry information from collisions of black holes. So in the last couple of years, we've entered a new age of astronomy where we can watch black holes collide. To reverse, Stephen Hawking's area theorem, which seems to have been proved by these collisions now, says that if you collide two black holes together, then the area of the horizon around the new black hole has got to be bigger than the area of the horizons of the two little black holes. And that seems to be what we've seen. What is that thing, the event horizon? It's the area around the black hole from which light can't escape. So if you go into a black hole, which you could do if it's sufficiently big or sufficiently massive, you could fall in through this point, this sort of region of space around the hole. And you could easily fall in. What would happen when you fall in is that you could never get out again. And you couldn't even send a signal of light out of the black hole because the gravity is so strong that the light can't escape. And the region from which the light can't escape is called the event horizon, or inside this event horizon. And that's what you see with the black hole. If you could float around and see one, you wouldn't see anything because it would be black, but you would see this sphere or this shape in space from which no light would emerge, and around which all the light from the distant stars and the galaxies would bend and curve and be warped. So that's it. It's a very strange thing, a black hole. And I should also say, we don't know what happens right in the middle. So it's called the singularity. That's where our physical theories break down, and that's another thing for you lot to go and do. Probably someone of your generation will work out how to do the physics to say what really happens in the middle.
I mean, it is. He doesn't like inflation as a theory.
He doesn't?
Oh
no.
But it's right that our universe is accelerating in its expansion at the moment, which is one of the great mysteries that was discovered in the 1990s by a friend of mine, actually. Brian Schmidt got the Nobel Prize for this discovery. He told me once, I don't know if I told you the story before, but he told me that he'd made this measurement, and it wasn't really. He was looking at supernova explosions, and he'd seen that the suggestion in the data was that the universe is accelerating in its expansion, not slowing down, but speeding up in its rate of expansion. And no one was expecting it, so he thought it was just wrong. But he couldn't find anything wrong with his data. So he published it and thought, well, that's the end of my career.
Oh, boy.
He was quite young. I think he might have even been a postdoc, and he just published it. He thought, that's a good scientist, right? I don't think this is right, but I can't see anything wrong with it. I'll publish it. Someone else will tell me where my mistake was. And there was no mistake, and he won the Nobel Prize.
Wow.
For that discovery. That's the 1990s. So this idea the universe is accelerating in its expansion, the way that it does that is really important. Is it going to carry on doing that? Is whatever's driving that expansion going to change in some way, which could actually recollapse the universe again? We give it a name, by the way, dark energy, this thing, but we don't know what it is. I think it's very fair to say. But it looks a bit like inflation, but it's way slower. So maybe they're linked, maybe it's the same kind of thing. We don't really know. And so it's one of the great mysteries. So, but the universe, it looks like the universe is going to continue to expand forever and to continue to accelerate. In brackets, I am. It's really easy to explain, actually. Dark matter, when we look out into the universe, we see lots of things. For example, the speed that galaxies rotate, or the way that galaxies interact together, or actually the oldest light in the universe called the cosmic microwave background and patterns in it, which are suggestive of there being some kind of particle. So that's like this stuff, like electrons and things, but some kind of particle that's quite heavy and does not interact with light. So that's why it's called dark matter. You can't see it because it doesn't interact with photons, but it dominates the universe, 5 times as much of it as there is of this stuff, out of which everything we can see is made. So that's what dark matter, the best theory for it. We see it by its gravitational interaction. However, it's not shown, it's not proven that's the case because we haven't detected the particle. And there are experiments everywhere in underground labs and so on, and at Large Hadron Collider at CERN, where we're looking for these things, but we haven't seen them. And so that leaves open the possibility that there's something else going on that we don't understand. Yeah, dark matter's in some sense, marginally less confusing in the sense that at least we have an idea of what it might be. Whereas dark energy, there are people listening to it, there are people working on it, so there are theories about what it might be. But I think it feels less explicable given what we know than dark matter, but we haven't discovered what we think dark matter might be some kind of particle that is got certain properties and doesn't interact very strongly. It interacts like neutrinos, basically, that you mentioned earlier. So really doesn't interact very strongly. But we thought we might have seen those particles. We're looking for them. They would be passing through this room now, and so we could build a detector in here, and we do that, and we look for these particles. We haven't seen them. We thought we might make them at the Large Hadron Collider at CERN. I think many people thought that we'd see the signature of these things, and we haven't done. So it could be that we're not right with that picture. So it's about 5% matter, about 70% dark energy, and the rest, so 25% dark matter. So we're just less than 5%. This
that's crazy.
Us. So and stuff we can see. So everything we can see in the sky, all the gas and the dust and the galaxies and the stars and the black holes, all those things, less than 5%. According to the standard model of cosmology.
And so the other 95% is just like
something else.
knows, something else.
Yeah, and
wow.
So, but those are models. I mean, it's important to say that it's interesting because so we have a hypothesis which is strongly supported by lots of bits of evidence that dark matter is some kind of particle. So that's what you'll find in the textbooks. But it's true that until you find it, until you see it, then you haven't shown it to be correct.
Are there alternative theories?
There are, and they're not...
Are they compelling?
No, they all have problems, and most of them have problems with that pattern, the CMB, the cosmic microwave background that we just saw. Because that pattern, what you're looking at actually in that pattern is acoustic, it's waves, sound waves essentially, in the early universe that go through the plasma of the early universe. And they go out, and we know what speed they go through that plasma. So it's almost like you're looking at a pond and you're throwing stones into the pond. And they all land in the pond at the same time and send ripples out, little circular ripples in the pond, and they all overlap. And that's what that pattern is. So we're looking at sound waves going through this plasma. And those theories require the dark matter. The dark matter fits well if it's in there, in this plasma, in this kind of soup, this subatomic particle soup that's the early universe. And the way the sound waves go through it fit that idea. So that's one thing. But the idea also came from looking at galaxies and how they rotate, and galaxies and how they bend light and deform space and time, and how they interact together. So there's loads of different bits of information, observations of the universe, from the cosmic microwave background all the way through to galaxies, and the formation of galaxies and the theories that we have there that suggest there are these particles around that interact very weakly with light. So they don't really interact with light at all, which is why we don't see them, which is why they're dark. That's just like a neutrino, right? So like heavy neutrinos. And actually there was a theory once that maybe they were heavy neutrinos, but that's kind of disfavored now. And so we have loads of kind of different bits that fit. This is how you do science. You start with a theory and you make a load of observations and you can infer things and you get a consistent picture. But very importantly, until you find it, until you really find that particle, then you don't know. And we've inferred it. So you might say, how do you know it's there? Which is a good question, right? I mean, if we've not detected this stuff, how do you know? And it's from Einstein's theory, really. So it's from gravity. It's from looking at the way that galaxies rotate and the way that these sound waves move through the early universe and the way that the universe expands. Because the way the universe expands is related to the stuff that's in the universe. So we can weigh the universe and find out what kind of different things are in there by looking at the way it's expanded and how that expansion history has changed over time. So it's all what you do with science, which is why it's true that you can criticize any one bit of it, And people will. So online, you'll see in the comments under this, there'll be people saying, what about this? What about this? What about this?
Sure.
And it's true that you can pluck away and pick away at any piece of it. But the way it tends to work is when you have this kind of consensus view of something, it's because you have multiple observations that all fit a particular hypothesis. And by changing one of them, by changing the explanation of one of them, you tend to mess the whole other thing up. You mess the wider description of multiple phenomena up. You mess it all up. So it's quite hard to find other theories at the moment that will fit all of those different observations. I mean, another example would be the age of things. It's interesting that we can measure the age of the Earth, right? And you measure it from geological processes, radioactive dating and so on, and you can kind of measure the age of the Earth. You can measure the age of the Sun in a different way. You can measure it by looking at called helioseismology. So you can measure how much helium is in the core of the Sun. And the Sun shines by making helium from hydrogen. So by measuring the amount of helium in the core, by looking at basically sound waves, it's like an earthquake, but sunquakes, you can measure how much helium's in there, so you can get an estimate of the age of the Sun. And then you can get an estimate of the age of the universe by measuring how it's expanding and using Einstein's theory. The fact that they all fit with the picture of a universe that's 13.8 billion years old, a sun that's 4.5 billion years old, a planet that's 4.5 billion years old, the fact that it all fits is it's quite an intricate model. And so you could say, well, I argue with the measurements of the age of the Earth. Maybe I don't like the radioactive dating or something, and people will say that. But the thing is, it's a consistent picture with multiple different observations. And same with dark matter. So the standard model of cosmology is you have, as I said, about 5% matter, 25% dark matter, 70% dark energy. It might be wrong, but it fits loads of different independent observations. So it's a consistent picture. How will the universe end? Well, the current best guess or best estimate is that it will carry on expanding forever. And the reason I say that is because actually one of your great scientists in Australia, Brian Schmidt, got the Nobel Prize for discovering that the universe is accelerating in its expansion, which is a great mystery, because before that discovery we thought, well, gravity is always attractive, and so it should be, we've got all these galaxies in the universe, and the universe has been expanding since the Big Bang, and so it should at least be slowing down. And there was even a question as, is there enough matter in it to slow it down so much that it stops and recollapses again? But this new discovery, it's only a decade old or so, that the universe is accelerating in its expansion, suggests that it will continue to accelerate unless some new physics appears that we don't understand, and so it will just continue to expand forever. These are brilliant questions. It's one of the fundamental questions in modern theoretical physics. It's interesting, this idea of the Big Bang created the universe. That's what Einstein's theory says. That's textbook cosmology, if you like. But the current textbook picture is there was a phase in the universe's life before the Big Bang, if you define the Big Bang as the hot, dense phase from which the universe appeared to sort of burst forth 13.8 billion years ago. And that phase is called inflation. So what we think happened is that before that, the universe was accelerating exponentially fast. It means it was doubling and doubling and doubling in size. And the numbers are ridiculous. We think that if you started with a universe that was smaller than a single atom, then it would be bigger by a long way than the whole observable universe, with 350 billion galaxies in it, in less than a millionths of a second. For those of you that know scientific notation, it's something like 10 to the minus 35 or 10 to the minus 36 seconds. So a very rapid, exponentially fast expansion. And when that stopped, all the energy that was driving that expansion got dumped into space. It heated it up. It produced the particles of matter out of which we're made and all the things that we see out there in the sky. And that's what we see as the Big Bang. So that sounds fanciful, but that's standard cosmology at the moment. The big question then is, well, what started the inflation? What stopped the inflation? How long did the inflation go on for? And the answer to that is, we're not sure. We don't know. And I'll just say one last thing. Some of those theories suggest that the inflation doesn't stop all at once. It stops in patches. And every time it stops, you get a universe. And so some of these theories, they're called eternal inflation theories, suggest that there might not be just our universe, the bit that we can see, but there might be many universes, perhaps an infinite number of them, and they may be being produced all the time. So that's what to make of that, but that's where current modern cosmology is.